Okay, so this topic is going to be about vectors. You've covered vectors a little bit at GCSE. We're just going to expand on that a bit more at A-level. So there's the reference grids for you to see where to get questions from. So again, the Edexcel textbook, the AQA textbook, or the Solomon sheet. Okay, just to recap. So we should know that a vector has two properties. It has a magnitude, which just means its length, so how long is this vector, and it has a direction. So what direction is the length going in? In contrast to that, a scalar is just a length. So if I'm talking about a scalar, I'm just talking about a length, so just a number. I'm talking about a vector, it's a number with a direction. So for example, the main use of vectors at GCSE would have been for translations. So you would have said stuff like 2 right, 3 up. So each of those steps had a distance or length and a direction. So 2 left, 3 up, for example. Displacement is a vector, but distance is a scalar. So you would say I've travelled 5 kilometers, that's the distance. You would say I've travelled 5 kilometers northeast, that's a vector, that's a displacement. Same thing with velocity. Velocity is the vector and speed is the scalar. So I'm traveling 30 miles per hour, that's the speed. But I'm traveling 30 miles per hour in the north direction, that's a vector, that's velocity. Our notation, if it's typed, we normally use bold, so like this here. And if it's handwritten, we normally underline it, because obviously we can't write in bold. And if we use a vector to describe a translation from one point to another, we can just use an arrow notation. So if I want to say go from point A to point B, I can just put an arrow on the top. Now, the most common vectors we'll write when we talk about displacements are i's and j's. So I is the unit vector, so that means 1 to the right. So 1 horizontally to the right. And j means 1 up. So it's kind of like x and y. So if you think of these as axes, so I think of your normal graph, x and y. I is 1 along the x-axis, and j is 1 up the y-axis. So I can write any 2D displacement vector. So if I just call it xy, I can write that as xi plus yj. So x in the horizontal direction plus y in the vertical direction. We can extend on that to 3D. So for 3D we have x, y, and z. So the same thing, I can write a 3D vector, so x, y, z as xi plus yj plus zk, where k, as you guessed it, means 1 in the z direction. So there's the vectors for I, j, and k. Okay, the first thing we'll look at is how do we find out the magnitude and direction of vectors? Well, the magnitude, which again we could call a modulus, you might have heard that word already, of a vector is just its length. And the direction, we normally choose the direction to be the angle and makes with the positive x-axis. However, there are some exceptions. They could ask you to work out bearings, for example. So just read the question carefully to see which direction it's measuring from. Is it from the horizontal axis or is it from the vertical axis? So here I've got P, Q, and A making a triangle. So I could say the vector A is P plus Q. And the magnitude of A, well, I would just use Pythagoras to work it out. I would do P squared plus Q squared and then square root it. And to work out the angle, I can just use trigonometry, so SOHCAHTOA, to help work out the angle. So we normally have opposite and adjacent, so I can work out that angle there by using tan. So some examples here. So calculate the magnitude and direction of each of the following vectors. So I'm always going to start off just by sketching them. So A goes 4 to the right and then 3 down. So here's the length. I'm going to put the arrow on it, so that's my vector there. So to work out the length, so the magnitude, I do square root of 4 squared. Now, I could write plus minus 3 squared, as long as I have the minus 3 in brackets. But when I square negative, it just turns positive anyway. So I'm just going to put plus 3 squared, which gives me root 25, which gives me 5. So the length is 5. And to get this angle here, I'm going to do tan of the angle is opposite, so that's 3 over adjacent. And then to get the angle, I'm going to do arctan, so the inverse of tan. I'm going to make sure I'm in degrees, and I get the angle is 36.9 to 1 decimal place, and it's below the horizontal. So that means that angle's underneath the horizontal, it's not above, it's going down. Okay, so you might want to have a try the rest yourself. So you might want to pause it and try the next 3 yourself. Okay, number 2. So again, I'm going to start off with a quick sketch. So it starts here. I go 9 to the left. It's negative, so it goes backwards, and 12 up. So there's my displacement. So to get the length, I'm going to do square root 9 squared plus 12 squared, and square root it, and I get 15. So the magnitude's 15. And to get the angle, well, I measure from the positive x-axis, so it's this angle I want. So what I'm going to do is I'm going to work out this one and then just take it away from 180. So to get that angle, I'm going to use tan theta is opposite over adjacent, and then do arctan to get what that angle is. So I get 53.1 degrees. So then the red angle, we'll do 180 minus that, which gives me 126.9 degrees. And again, it's above the horizontal this time. So the last one was below because it was going down. This one's above because it's above that horizontal line there. Okay, the third one. So I'm starting somewhere here. I'm going 1 to the left, it's minus I. I'm going down by 2, it's minus 2j. This length here, I'm just going to do the magnitude. I'm going to do 1 squared, add 2 squared. So I get the magnitude is root 5. And the angle, well, I want this angle here. Because the angle I want is this red angle here. Because if this is the positive horizontal axis, I want this one here. So I'm going to do tan theta is opposite over adjacent. So I'm going to do arctan to get that angle there. When I've called theta is 63.4. And I'm going to take that away from 180. To get it's 116.6 degrees below the horizontal. And last one, so 5 to the right, 17 up, so there's my distance. So the magnitude is square root 5 squared plus 17 squared. Square root, so I get, that's root 314. Then to get the angle, It's going to be nice and simple this time because it's just going to be that angle. So I do tan theta is opposite, so 17 over 5, do arctan of 17 over 5, and I get the angle is 73.6 degrees above the horizontal. Okay, so hopefully you get an idea. It's Pythagoras. It gives me the magnitude, the length, and I use SOHCAHTOA, mainly tan, to get the direction. Let's look at an example where we've got the length and the direction and we want to get the vector. So it says a vector has length 10 and its direction is on the bearing of 0, 6, 0. So first of all, let's draw that bearing. So remember, I need to start from the north line. I measure clockwise, so 60 degrees clockwise, and I go 10 along. So this length here is 10. Okay, and now I want to get the vector, so that means I need the horizontal distance, which I'll call x, and the vertical distance, which I'll call y. If this angle here is 60, then this one here is going to be 30 degrees. So the one to the horizontal is 30. And then we use SOHCAHTOA now to get x and y. So if I look at the one with x in, then I know that cos 30 is the adjacent, so that's x over the hypotenuse, which is 10. So I can rearrange that to get x is 10 cos 30. And I can type that in my calculator to get x is 5 root 3. I can do the same thing for y, so that's opposite, so I'm going to use sine. So sine 30 is the opposite over the hypotenuse, so y over 10. So I can times both sides by 10 to get y is 10 sine 30, which I can just type in my calculator and just get y is 5. That's a vector. I can write it as a column as 5 root 3, 5. Or I can write it in terms of i's and j's. So I can write 5, 3, I plus 5. Yeah, I prefer the columns. So mathematicians normally use columns. Engineers and scientists normally use the i's and j's. But it's completely up to you. We can extend this idea to 3D. So we don't talk about directions too much at A level in 3D, but we do talk about lengths. So the length is just Pythagoras still. So the first example is 3D still. So to get the length, and we use the two lines to denote the length. So these two lines just means length. So I use Pythagoras. I do 3 squared plus 7 squared. So that gives me root 58. And for this one, I do square root 3 squared. Again, I'm going to put plus 2 squared, because when I square, negative turns positive anywhere. Plus 5 squared. So I get root 38. Yeah, same idea. So I don't think you'll need to practice that much if you get the idea of the 2D one. Now, unit vectors is a special type of vector. It's where the length is 1. Unit just means 1. Yeah, so this word here, unit, just means 1. So we say a vector is a unit vector if the length is 1. So which of those two vectors, if any, is a unit vector? So you would have to work out the length. So for A, I do square root 1 squared, add 2 squared, so root 5. So that's not a unit vector. Root 5 is not 1. Whereas for B, it would be square root 1 over root 3 squared plus root 2 over 3 squared, which does give me 1, so that 1 is a unit vector. And for part B, find 2 possible values of t such that c equals 12ti minus 9tj is a unit vector. Okay, so it's a bit of problem solving. So straight away I'm going to highlight 2 possible values. So I'm looking for 2 answers, and I want it to be a unit vector. So if I convert that into a maths statement, so a unit vector, that means the magnitude of c is 1. So to get the magnitude of c, I would square the I component, square the j component, and again I'm going to ignore the minus and add them. So that's going to equal 1. And I can just simplify it, so I get 144 t squared plus 81 t squared square rooted equals 1. I can keep simplifying it, so 144 add 81 gives me 225. T squared is 1. Okay, then if I give the square root by squaring both sides, I get 225 t squared is 1. I can divide both sides by 225, so t squared is 1 over 225. And then I can square root both sides, and when I square root 1 I get 1, when I square root 225 I get 15, and since it's t squared, I mean I can have a plus or minus in my answer. So 2 answers for t, 1 over 15 and negative 1 over 15. You could always sub those back in to see and check. So 1 would be 12 over 15 minus 9 over 15 with my i's and j's, and at least you've got them there, which actually if you simplify that you just get 4 over 5i minus 3 over 5j. And if you could do Pythagoras, you might spot the 3, 4, 5 triangle. Or the other one, if I subbed in minus 1 over 15, we get minus 4 over 5i plus 3 over 5j. Yeah, and you can just double check that the magnitudes of those is 1. Yes, this might be a good time to stop and do some practice. So from exercise 15A in the AQA textbook. Okay, the next little bit we're going to talk about is operations with vectors. So as you can see in the diagram, I've got a vector A and a vector B. Now on the grid opposite, I'm going to show the vector A plus B. So with vectors, plus just means one followed by the other one. So if I start off by doing A, so I'm going to start off somewhere to the left, so let's start kind of towards the bottom as much as I can. So let's start here. So A goes 1, 2, 3, 4, 5 across and 2 down. So 1, 2, 3, 4, 5, 2 down. So here's A. And then B goes 2 across and 4 up. So 1, 2, 2, 3, 4. So this vector here is B. So the vector A plus B is the result starting from what my starting point, ending in my finish point. So this red vector is my vector A plus B. Yes, that's how I can do it as a picture. I can also do it using numbers. So I can write A as a column vector. So A was 5 to the right and 2 down, so 5 minus 2. B was 2 to the right and 4 up. So when I add them together, I get 7 to the right and 2 up. Now let's just check. 1, 2, 3, 4, 5, 6, 7. 1, 2. Yeah, so I get the same answer by using arithmetic as I do from using a diagram. So A plus B just represents one vector forward by another, and minus a just represents the same vector, just in the opposite direction. So if a is going this way, then minus a is the exact same vector, just going the opposite way. Now, scalar multiplication just means multiplying by a number. So it just changes its length. The direction stays the same, it just gets stretched, so longer or shorter. So for example, if I have a vector, so a, which I'm saying is 5 minus 3, and I want to get 2a, then I just have to times my vector a by 2, so I get 10 and minus 6. Yeah, so each component just gets times by the number, so it's nice and straightforward. So let's jump into a nice problem solving question, because you've probably seen all this vector stuff in year 11. So given that a times the vector 2, 3 plus b times the vector minus 1, 5 is 15, 55. Let's find the values a. Well, first of all, I know that if I times the vector 2, 3 by a, I just times 2 and 3 by a, so I get 2a and 3a. And if I times the second one by b, I just get minus b and 5b. And that has to, when I add them together, that has to equal 15, 55. Now I know to add vectors, I can just add the top ones together, add the bottom ones together. So I get 2a minus b on the top, and 3a plus 5b on the bottom, which gives me the vector 15, 55. And if two vectors are equal, that means each component must be equal. So the I component must be equal. So I get the equation 2a minus b is 15, and the j component must be equal. So 3a plus 5b equals 55. So solve that however you want to solve. Remember your calculator will solve simultaneous equations for you. So if I just stick in my calculator, I'll get very quickly the answers. A is 10, B is 5. Now it's always good when you get your answers to check by subbing them back in and seeing if it works. So if I did 10 times that first vector, I get 20, 30. 5 times the second one, I get minus 5, 25. I want to add those together, will I get 15, 55? Yes, I will. So I'm confident I've got full marks on that question. Okay, next little thing to look at are equal and parallel vectors. So vectors are parallel if they're multiples of each other, so scalar multiples of each other. So if I can times one of them by a scalar and get the other one, then they're parallel. So that means they're the same direction, just different lengths. And vectors are equal if they're parallel to each other and they have the same magnitude. So that means the components are equal. So the horizontal component, vertical component, they're equal. So given that P and Q are not parallel, state whether or not each of the following pairs are parallel. So have a think about these 6 pairs here. See if you can spot which ones are parallel yourself and which ones aren't. So pause it and take a guess out of the 6, or not take a guess, sorry, try to see if you can work out which ones are, which ones aren't. Okay, so for A, there are, and it's because I can write 3p, I can write that as 2p if I times it by 3 over 2. So the 2 on the bottom, the half, cancels out the 2 times by 3. B is not, because to get from p to 2p, I would have to times by 2. But if I times 2q by 2, I should get plus 4q. I get a minus, they're not. C, well, to get from 3p to p, I need times by a third. And if I times minus q by a third, I get minus third q, so that one does work. So C is parallel, because I can write 3p minus q, I can write that as 3 lots of p minus a third q. D, now be careful, there's p's swapped around there, look. To get from p to minus 2p, I times by minus 2, and to get from minus 2q to 4q, I times by minus 2. So D is, and B, I can write that 4q minus 2p, I can write that as minus 2 lots of p, take away 2q. E, to get from 3 over 4p to 6p, I need times by 8, and to get from q to 8q, I need times by 8 as well. So E is, because I can write the second one as 8 times the first one, and then F, well, to get from 2q to 3 over 2q, I need to times by 3 over 4, but if I times minus 3p by 3 over 4, I don't get minus p. That's not. Okay, got another example here. So I've got two vectors. A is 1, 2, and C is minus 2, 5. And it says find the value of scalar k. So k is a scalar, so that just means it's a number, such that A plus C, kc, is parallel to the vector 10, 23. Okay, well, to do this one, I'm just going to do it bit by bit. So let's write down what A plus kc would look like. So I'm going to have on the top 1, then I'm going to times k by c by k, so I get 1 minus 2k, and on the bottom I'll get 2 plus 5k. So that's my vector. Now it's parallel to 10, 23. So they're not equal to each other, but it's equal to that times the scalar. So I've already used the letter k, I've used the letter a, c, so let's use n. So I can get two equations from that. So looking at the top component, I get 1 minus 2k is 10n. And now looking at the bottom one, I get 2 plus 5k is 23n. Now a good way to solve simultaneous equations like this is I can divide them to get the n's to cancel out. So if I just do the top one divided by the bottom one, I get 1 minus 2k over 2 plus 5k is equal to 10 over 23 because the n's cancel out. Now if I times both sides by 23 and 2 plus 5k, you might call this cross multiplying. I get 23 lots of 1 minus 2k equals 10 lots of 2 plus 5k. And then just solve it. So 23 minus 46k is 20 plus 50k. And then keep solving it. So I get 3 equals 96k. So k equals 1 over 23. Yeah, you could always solve it using simultaneous equations. So if you want to use a calculator, you need to get it written in the form where it looks like 10n plus 2k equals 1 and 23n minus 5k equals 2, because you need the letters all on one side. So if I type that in as well, 10, 2, 1, 23 minus 5, 2. Then that shows me I've made a silly mistake here. 96 divided by 3 is 32, not 23. I got my 3 and my 2 the wrong way around. So my calculator is telling me that n is 3 over 32 and k is 1 over 32. Now we don't care what n is. I don't care what this number is here. It just wants the scalar k. Yeah, so let's talk through those steps again. We wrote down what a plus kc look like. Now I know it's parallel to 1023, so it's not equal to 1023. It's equal to 1023 times a number. So it's 10n and 23n. Now I could have used any letter I wanted. I just thought of n. I could have used B. I could have used any letter in the world. I could have used a Greek letter, if you like Greek alphabet. And the last one, find 2 unit vectors parallel to 3, 4. Well, let's call the unit vectors, let's call it A. And if it's parallel, I mean, it's going to be 3 times something and 4 times something. So I'm going to use a different letter now. In fact, I'm going to use a Greek letter now. I'm going to use lambda. That's one we use quite a lot in maths. So that's what I want it to look like. I want it to be a unit vector. So that means the length has to be 1. So if I do 3 lambda squared plus 4 lambda squared, that equals 1. So I can simplify the bracket to get 9 lambda squared plus 16 lambda squared equals 1. Square both sides. So I get 9 lambda squared plus 16 lambda squared is 1. So 25 lambda squared is 1. So lambda squared is 1 over 25. Square root both sides. I get 1 over 5. And I can have a plus or a minus. So that's where I get 2 answers from. So one possible unit vector is 3 times 1 over 5. So 3 over 5, 4 over 5. And the other one is minus 3 over 5 minus 4 over 5. Yeah, so parallel means it's times by number, and unit means the length was 1. So there's the 2 key facts we use in this example. Okay, let's try putting these skills together with 3D vectors. So I have 3 vectors, A, B, and C. And as you can see, in C, no pun intended, there's two unknowns, P and Q. So part A says, find the values P and Q such that A is parallel to C. Okay, well, A and C are parallel. That would mean that vector A is equal to something times C. So I'm going to say, if I times A by lambda, I get C. Or equally, I could times C by lambda. So I get, if I times A by lambda, I just chose to times A by the number because A's got all known constants. So I get lambda, 2 lambda, and 7 lambda. And that's equal to C, so that's minus 2 P and Q. So from that, I look at the first row, so the I component, I get lambda is minus 2. If I look at the second component, the J's, I get P is 2 lambda, because I know that lambda is minus 2, so P is 2 times minus 2, so P is minus 4. And if I look at the third row, I get Q is 7 lambda, but again I know that lambda is minus 2, so Q is minus 14. So there you go, P is minus 4, Q is minus 14. And part B says, find the value of the scalar m such that A plus MB is parallel to this vector here. So again, if I write down what those key facts mean, that means that A plus MB is equal to that vector there times by constant. So I'm not going to use lambda. Think of a Greek letter. Let's use Let's use mu. So 0 times mu is just 0. 10 times mu is 10 mu. And 23 times mu is 23 mu. So now if I work out what the left-hand side looks like, so I get A plus MB, so 1 minus 3M, 2 plus 4M, and 7 plus 2M. That must equal 0, 10 mu, and 23 mu. Okay, well now I've just got 3 equations. So from the top one, I get 1 minus 3M is 0. So I get that 3M is 1, so M is a third. And in fact, that's all the question wanted. The question wanted find the value of M, and I found M. M is a third. If I wanted mu, I could sub in M is third into either the second row or the third row. Okay, so you might want to practice some of those skills to do with operations, so adding, parallel vectors, equal vectors, stuff like that. So if they're equal, I just make the vectors equal to each other. So if A and B are equal, then that means that A equals B. But if A and B are parallel, then that means A is equal to something times B. So I just used lambda. I just like the Greek letter lambda at the minute. Okay, now we're going to talk about position and displacement vectors. So we can think of a vector as a journey that starts at one place and ends at another place. So remember, it's a direction with a length. So it's getting from one place to another place. So a displacement vector only describes the journey. So if I know the position vectors of 2 points A and B, I can find the displacement AB. So looking at this triangle on the left, I've got O is just what we call the origin. So this thing here, it's used blue, that's my origin. So here's my position A, and the vector to get to it is little a. Here's my position B, and to get to it is little b. So to get from A to B, I have to go first to O. So I'm going along A, but the opposite direction. So it's negative A. And then I'm going along B, so positive B. So to get from A to B, it's negative A plus B, or as it looks better to write, B minus A. So it's the second one minus the first one. Yeah, you can link that a little bit to the integration. So I'm integrating between two limits. It's the final one, take away the first one when you sub numbers in. So it's the final position, so B minus the first one, so B minus A. Yeah, I can also write coordinates as position vectors. So if I have a coordinate, let's say I call it A, which is 1, 2, I can write that as a vector by saying if I start at the origin, then to get from O to A, I go along 1 and up 2. So simple as that, just 1, 2. Yeah, so if it's written as coordinates, that means it's horizontal with a comma, and if it's written as vector, it's vertical without any comma. So points A and B have coordinates 3, minus 1, and 5, 0. And part A wants us to write as vectors the position vector of A and B. So part A, I, we have O to A is just 3 minus 1, and OB, where O is just the origin, is 5, 0. Simple. For II, find the displacement vector for A to B. So using that little formula above, it's B, so O to B, minus A, so O to A. So it's 5, 0, minus 3, minus 1. So 5 minus 3 is 2. 0 minus minus 1 is 1. Again, you could have got that without doing any kind of subtractions by thinking, how do I get from 3 to 5? I have to go along 2. And how do I get from minus 1 to 0? I have to go up 1. So 3, 1. And part B is asking, find the position vector of the point C such that C to A is minus 4i plus 2j. Well, I'm first of all going to start off by writing that as a column. So I can deal with columns a bit better. C to A, using that same formula, is O to A. Take away O to C. So the final one, take away the first one. And I'm trying to find the position vector of C, so I'm trying to find O to C. I'm trying to find this thing here. Okay, well, O to A, I know that one was 3 minus 1. So 3 minus 1, take away O to C, is minus 4, 2. So to get O to C by itself, I'm going to add it on to the other side and then subtract that other vector. So it's 3 minus 1, take away minus 4, 2. Or you could just do, what do I need to take away from 3 minus 1 to get minus 7, 2. And I get 3 minus minus 4 is 7. Minus 1 minus 2 is minus 3. So my position vector for C is 7 minus 3. As a coordinate, it will be 7 minus 3 written like that. But as position vector, it's written as a column. Okay, the next one. You might want to try this one yourself. Points A and B have coordinates 3, minus 1, 2, 5, 0, 3. Write as column vectors the position vectors for A and B, and work out the displacement vector A to B. In fact, yeah, you could probably do all this yourself. So pause it, try this yourself, and check your answer. Okay, so hopefully you got the same answer. Next one. The diagram shows points M, N, P, Q, and we've got the displacement vectors between them all. Now, they're on the diagram, so I'm not going to read them out. Just be careful which way the arrows are pointing. So, find the following in the component form. So that means in terms of i's, j's, and k's. So M to P. So if I use different colors, so from M to P, I'm going to do M to N plus N to P. So if I add those two vectors together, I get 3i plus I is 4i, minus 2j plus j is minus 1j, and 6k minus 3k is 3k. Okay, let's use a different color for the next one. P to M. Well, that's just going the opposite way now. So it's just going to be minus M to P. So it's just minus 4i plus j minus 3k. And final one, P to Q. Well, P to Q, I can go P to M and then M to Q. So it's P to M, then M to Q. So if I add them together, so minus 4i plus no more i's is just minus 4i still. 1j minus 2j's is minus 1j, and minus 3k plus 5k's is plus 2k's. So it's minus 4i minus j plus 2k. Yeah, as a little rule, if I want to go, say, A to C, actually, let's do A to B. So you know that A to B, one way of thinking about that is it's O to B minus O to A. Another way of thinking about that is I can go from A to anywhere I want, so I'm going to call it X, and then X to B. Yeah, that's kind of where the first one comes from. So the first one comes from going A to the origin plus the origin to B, and A to O is just minus O to A. So that's how you get from that one to that one. Yeah, so if I want it, so to get from P to Q, for example, that's why I can go from P to M, then M to Q, as long as the middle two letters match. Okay, we've got all the skills we need now to talk about the distance between 2 points. So if I've got 2 points, A and B, and I can say position vectors, let's denote them as A and B as little letters, lowercase, then the distance between them is just the magnitude of the displacement vector between them. Yeah, so if there's A to B without an arrow, that means distance, whereas A to B with an arrow means from A to B. So to get from A to B, I would just do the magnitude of A to B, which is B minus A, remember. So I've got 2 points with position vectors in the next example. Here's A and here's B. Find the exact distance of AB. The first thing we do is work out A to B. So that's O to B, which is called little b, take away O to A, which is called little a. So if I do that, I'm going to do that as columns. So I get 5, 2, 3, take away 2, minus 1, 5. That's me 3, 3, minus 2. And so if I want the distance, I'm going to do the magnitude of 3, 3 minus 2. So it's square root 3 squared, add 3 squared, add 2 squared. So I get root 20. That's it. Simple as that. So I get the displacement between them and then just do the magnitude. Okay, next one. Find the distance between points A and B with position vectors A and B. So you can do part A yourself. So give my voice a pause and try it yourself. And hopefully you got root 5 as well. Okay. B. Point C has position vector 2p and says find the exact values, so multiple, and exact means in terms of square roots, such that AC is 3 times AB. Well, I've worked out AB was root 5, so I can do 3 times AB is just 3 root 5. So the left hand side gives me, if I just root that off, gives me 3 root 5. And to get AC, that I do the magnitude of C minus A. So that's the magnitude of C is 2p, minus A is minus 3, 2. That needs to equal 3 root 5. So if I work that out, 2 minus minus 3 gives me 5. P minus 2 is just P minus 2. I can use Pythagoras now. So square root 5 squared, add P minus 2 squared is 3 root 5. I can square both sides, so I get 5 squared, add P minus 2 squared is, if I square that side, I get 9 times 5 is 45. So I can simplify it. 25 plus P minus 2 squared is 45. I can take away 25 from both sides. So P minus 2 squared is 20. I can square root both sides. So P minus 2 is, when I root 20, I get 2 root 5. And since it's a square, I get plus or minus, and then plus 2 to both sides. So 2 plus or minus 2 root 5. Equally, you could have got that same answer by this point here. You could expand all that, get a quadratic, and solve it. It's just a bit quicker. Kind of, if I have it in completed a square form, it's easier just to rearrange from there. If there's only one P, it's easier to do that. So there you go, there's my exact values of P, 2 plus or minus 2 root 5. Okay, and the last bit of vectors is do vector representation again. So using vectors, talk about straight lines, 2D shapes, especially quadrilateral, stuff like that. So on the picture on the screen, you can see parallelogram. So parallelogram means each side, opposite sides are parallel. So A to B, this vector here, A to B is parallel to this vector here. So A to B would equal the vector D to C, for example. And A to D would equal B to C, for example. And if it's a rhombus, then the lengths would all be equal. Yeah, so they're common quadrilaterals that you might have to prove facts about. Okay, now straight lines. If I have 3 points on a straight line, A, B, and C, then that means if they're on a straight line, the vector A to B and the vector B to C must be parallel. So I can write it as B to C must equal something times A to B. So here they just use the letter T. And that can help me work out the ratio between the lengths A to B and B to C if I needed that. And if 3 points lie in a straight line, we call them collinear. Okay, so let's jump straight into an example. So 3 points have coordinates -3, 2, 6, 5, and 12, 7. Show that A, B, C lie in a straight line. Obviously, you can still do this without coordinate geometry stuff. However, I'm going to show you how you can do this using vectors. So for part A, what I can work out is I can work out the vector A to B. So that's B minus A, so 6, 5 minus -3, 2, which gives me 9, 3. And if I work out B to C, that's C minus B. So I get 6 and 2. And to show they're parallel, I can say that a third of AB is 3, 1, and half of BC is 3, 1. So therefore, a third of AB equals half of BC. So AB equals 3/2 times BC. So therefore, they're parallel. and if they're parallel, so parallel, so A, B, and B, C are parallel, so A, B, C are on a line. Because if they're parallel and they have a connecting point, they have the point B in common, they must make a straight line. Find the ratio AB to BC. Well, if BC is 1, then that means AB would be 3/2 times 1, so it'd be 3/2. So I can leave my ratio as that, or I can times both sides of the ratio by 2 just to get 3, 2 like that. And it's easy to see from the numbers where the 3 and the 2 kind of can come from. Okay, let's do some problems with midpoints. So you probably would have done this at GCSE as well. So just like coordinate geometry, if I want to get the midpoint of two coordinates, I would add the x's together, divide by 2, add the y's together, and divide by 2. Well, the same with vectors. If I want the midpoint of two position vectors, let's say A and B, where the vector to get to A is A, vector to get to B is B, to get the midpoint of A and B, I just add together the vectors A and B, and then half it, so divided by 2. Yeah, so exactly the same as coordinate geometry, just now this is more general, because this could work in 3D or higher dimensions. So let's look at an example. We have A, B, C, have position vectors A, B, C, lowercase. Find the position vector of D such that A, B, C, D is a parallelogram. So first of all I'm going to do is I'm going to sketch a parallelogram. So A, B, C, and D. Yeah, so when you label it, I'm labeling clockwise, A, B, C, D. Now, I don't know what D is. However, I do know that A to D, B, A to D, sorry, it's better. This vector here, A to D, must equal this vector here, B to C. Okay, so let's work that out. So A to D is D minus A, and B to C is C minus B. Let's stick the numbers in. So I get D minus A was 3 minus 5, C was minus 3 minus 1, and B was 4, 2. So I get D minus 3 minus 5. If I work that out, I get minus 7 and minus 3. So D, if I add that on, I get minus 3, minus 7 minus 3, plus 3 minus 5. So D gives me minus 4 and minus 8. It wants the position vector, so there we go, minus 4, minus 8. Now, I could have done that. Instead of using A and D, I could have used that here. This C to D is equal to B to A. I could have done that as well. That equally would have worked. Okay. Now in the question for the next part, it says M is the midpoint of the diagonal A to C. So let me just draw on A to C, and M is in the midpoint, so M's here. Find the position vector of M. Well, using the formula I told you about to get the midpoint, I'm just going to add the two vectors and divide by 2. So I'm going to do A at C and half it. So my midpoint, which I'm just calling M, is half of A was 3 minus 5 plus C is minus 3 minus 1. So M is half of 0 and minus 6. So m is just 0 minus 3. Yeah, and again, you can look at it and think, well, if m is in the middle of A and C, then look at the numbers here. What's in the middle of 3 and minus 3? It's 0. And what's in the middle of minus 5 and minus 1? It's minus 3. And finally, show that m is also the midpoint of B and D. Well, let's find the midpoint of B and D. So the midpoint of B and D will be half B add D. So half B was, let me go back and check, 4, 2. And D was minus 4 minus 8. So that gives me half of 0 minus 6, which again gives me 0 minus 3, which was m. So m is the midpoint of B and D. So what we've proven is the diagonals bisect each other. They cut each other in half. So the diagonals of a parallelogram bisect each other. So that's a fact you probably knew with GCSE, and we just use vectors to prove it in this specific case. Next one, we have points A, B, C, D with position vectors A, B, C, D, and E is the midpoint of B, C. So straight away, before I read any more, I'm going to write that means E is half B plus C. Oh, and look what part A is asking. Find the position vector of E. Well, E is going to be half B, which is 5, 0, 3, plus C, which is 7, 8, minus 3. So E is half. 5 add 7 is 12. 0 add 8 is 8. 3 add minus 3 is 0. And when I half that, I get 6, 4, 0. There we go, nice and quick. And again, looking at the numbers, that should be nice and easy. What's in the middle of 5 and 7? 6. What's in the middle of 0 and 8? 4. What's in the middle of 3 and minus 3? 0. Show that A, B, E, D is a parallelogram. So again, let me sketch that. And label clockwise. So A, B, E, D. So to show it's a parallelogram, I need to show that B to E is equal to A to B, and that A to B is equal to D to E. Okay, so let's work these four out. So let's do A to B first. Well, that's B minus A. So I'm not going to write all the numbers out. So B minus A, so 5 minus 3 is 2. 0 minus minus 1 is 1. And 3 minus 1 is 2. Then let's do D to E. So that's E minus D. So that's 6 minus 4 is 2. 4 minus 3 is 1. And 0 minus minus 2 is 2. So this shows me that A to B is equal to D to E. Okay, now next two, let's do B to E. So that's E minus B. So that's 6 minus 5, which is 1. 4 minus 0, which is 4. And 0 minus 3 is minus 3. And then let's do A to D, which is D minus A. So that's 4 minus 3, which is 1. 3 minus minus 1, which is 4. and -2 -1, which is -3. So therefore these two are equal. So BE is equal to AD. So therefore we have ABED is a parallelogram. Yep. Now that only worked because we labelled it correctly. When we label shapes, we have to go in the same direction. So I have to label them going around a circle like that. Yeah, I can't just label them in any order I want. So I can't say this is A, this is B, this is E, this is D. It needs to follow some kind of pattern. A, B, E, D. Like that. It doesn't matter where you start. So I could have started here, A, B, E, D, and I'd still get exactly the same answer. Okay, and final one. Two vertices of a triangle ABC. The vertices of the triangle ABC have position vectors ABC. M and N are the midpoints of the side AB and AC. So straight away, I'm just going to write that down. So M is a half A plus B, and N is a half A plus C. Oh, and that's what part A wants. A wants express the position vector of M and N in terms of A, B, and C. Done. Prove that MN is parallel to and half the length of BC. Well, let's work out what M to N would look like. So that would be N minus M. So that gives me a half A plus C minus a half A plus B. Well, I can factorize out the half and do A minus A gives me 0 A's, and I get C minus B. Yeah, so the A's will just cancel out. And then let's do B to C. That's just C minus B. Therefore, I have M to N is equal to a half B minus B, so it's a half BC. So therefore, MN and BC are parallel. But not just that, I've also got this half here. I know that MN is half the length of B to C. So MN is half the length of B to C. Yeah, so if I do a quick sketch of what that looks like. So here's triangle A, B, C. So M was midpoint here, N was midpoint here. So this length here, M to N, is half the length of B to C, and they're parallel. You can see that clearly. Okay, so now you can do all the practice on vectors and become very confident of using all the skills we've looked at.